Hi everyone and welcome back to the first module Windows Internals Overview in the Evasion Lab course by Altered Security. In today's part we will take a look at the kernel mode presentation of the process, starting by some general information about the kernel. So the kernel is a core component of the Windows operating system that runs in memory with the highest level of privilege. It acts as the bridge between hardware and user applications, ensuring system stability, security, and efficient resource management. Its primary responsibilities are process management. By managing the processes running on the system, controlling their execution and resource allocation, it ensures that each process has its own separate memory space, preventing them from interfering with each other. The second responsibility is privilege management. By managing the privileges between processes, enforcing strict access controls to ensure that no process can exceed its authorized permissions. And the third responsibility, the kernel also reinforces security barriers between processes, ensuring that they cannot access each other's memory or resources without explicit permission. The kernel operates in 128 terabyte system address space on x64 systems, ranging from 0xFFF8 all zeros to 0x all Fs. This address space is shared among all kernel mode components, including drivers and modules. The kernel tracks the state of each process using the eProcess structure, which resides in the kernel memory. The eProcess structure is a data structure that describes a process containing crucial information such as image name, token, protection level, threads, memory information. The eProcess structure changes across Windows versions as new features are added. To compare eProcess structures between versions, you can use the Virtualis project, a useful resource for security researchers and developers. Now let's take a look at some eProcess overview. The eProcess structure is a kernel memory structure in Windows that describes a process. It contains important information about the process, such as its identity, state, security context, and resources. Understanding the eProcess structure is essential for process analysis, debugging, and security research, particularly when dealing with process enumeration, privilege escalation, or PPL, protected process light bypassing. To get the eProcess address in WinDBG, the command !process 00 process name.exe will retrieve the eProcess address for the specified process. To get the eProcess field, the command !int eProcess, the eProcess address will display all fields within the eProcess structure like unique process ID, the PID of the process, image file name, the name of the executable associated with the process, useful for process comparison. The token represents the security token associated with the process, useful for privilege escalation or EDR's token downgrade. Protection shows the protection level of the process, indicating if it's a protected process PP or protected process light PPL, useful to bypass PPL protections. Active process links contains links to other processes, allowing enumeration of all active processes inherited from unique process ID, which helps identify the parent process that created this process. The PEP process environment block object table stores handles to kernel objects used by the process. Section base address shows the base address of the executable image in memory. Thread list head maintains a list of all threads within the process, useful to enumerate threads. Now let's take a look at process hiding and how we can manipulate active process links to do this process hiding. In Windows, active process links is a field within the eProcess structure that links all processes together into a double linked list. This list keeps track of every running process in the operating system, enabling process enumeration. Now let's dig deeper into the double linked list. The active process links field is of type list entry containing two pointers. The flink for word link points to the active process links of the next process in the list, and blink backward link points to active process links of the previous process in the list. This double linked list allows bidirectional traversal, making it easy to navigate through all active processes in the system. So how does it work? Every process has its own active process links field. The F link points to the active process links of the next process, while the B link points to the active process links of the previous process. The chaining mechanisms links all processes together, forming a circular double linked list. For example, in the illustration, process 1 F link points to the process 2, and process 1 B link points to the process 3. Process 2 F link points to the process 3, and process 2 B link points to process 1. Process 3 F link points to process 1, and process 3 B link points to process 2. To hide the process, attackers can unlink its active process links from this chain, effectively making the process invisible to system monitoring tools. This is a common technique used by rootkits. In this example, the goal is to hide the cmd.exe process. Here is how it's done. We have to identify the target process. The cmd.exe process is linked between process 1 and process 3. Its F link points to process 3, and its B link points to process 1. So the second step is to unlinking the CMD from the list. To hide cmd.exe, its active process links must be removed from the chain. This is done by modifying the pointers as follows. Process 1's F link is updated to point directly to process 3 by passing cmd.exe. Process 3 B link is updated to point directly to process 1, effectively closing the loop. After this change, cmd.exe's F link and B link are set to null, fully detaching it from the list. The result, cmd.exe is now invisible to tools that traverse the active process links lists, such as Task Manager and many security scanners and process monitors. The operating system continues to run cmd.exe, but it no longer appears in any process listing, making it effectively hidden. Now let's take a look at the token. In Windows, the token field within the eProcess structure defines the security context of a process. It contains the security identifier, the SID, user privileges, and group memberships, which collectively determine what resources the process can access and what actions it can perform. In this case, its offset is 0x4b8. The token is of type xFastRef that has the following fields. Object points to the access token object in kernel memory. Ref counts, reference counts, tracks how many components are referencing this token. When the reference count reaches 0, the token is released and freed from memory. And the most interesting field is the value, holds the actual token value. Now let's take a look at token and privilege escalation, how we can manipulate the token to achieve privilege escalation. In this slide, we will demonstrate how privilege escalation is performed in Windows by manipulating the token field within the eProcess structure. In this example, the cmd.exe process is elevated to system privileges by copying the token from the system process. The first command shows the eProcess address of the system process. The second command shows the eProcess address of the cmd.exe process. In the third command, we access the system token value from the system's eProcess at offset 0x4b8 in this case. In the fourth command, we change the CMD token with system token at offset 0x4b8 in the eProcess. In the fifth command, we display the new CMD token value, and we can see that it's changed to CMD token value. The operation will end up the CMD is running as NT authority system, the most powerful user on the system. Now let's take a look at how we can downgrade the EDR token by manipulating the token. Similarly, we can do the same and change the MS-MPENG token value to Explorer token value. effectively neutralizing its security capabilities. The MS-MPENG is running as anti-authority system. It has several high-level privileges enabled, like SE-debug privilege that allows the process to debug other processes and more. These privileges are essential for MS-MPENG.exe to monitor system activities, terminate malicious processes, and protect system integrity. After token downgrade, MS-MPENG.exe is now running under the user accounts, insurance, MKTG user 1. The process identity and permissions now match a standard user, effectively disabling all administrative capabilities. By downgrading the token, the process loses all system-level privileges, including its ability to terminate malicious processes or protect critical files, monitor system activities or inspect other process memory, respond to kernel callbacks, or interact with kernel mod components. Now let's see how we could bypass PPL and do an LSAS dump. So in Windows, the process protection level is a security feature designed to protect critical system processes from tampering, termination, and memory dumping. It resides in kernel as a 1 byte value and is part of the eProcess structure under the protection field. This protection level is represented by the PS protection structure, which is an 8-bit combination of the following fields. Type, which is 3 bits, defines the level of protection, like light or full. Audit, 1 bit, which is a reserved bit. Signer, 4 bits, identifies who signed the process, either LSA, WinTCP, or ONCHI malware. In this case, the protection field resides at 0x87A within the eProcess structure. In the screenshot, LSAS Local Security Authority Subsystem Service is marked as PS Protected Signer LSA Lite. This protection level prevents unauthorized access, including memory dumping, termination, and code injection. LSAS manages sensitive data such as user credentials and NTLM hashes, making it a prime target for credential dumping attacks like using Mimikatz tool. To prevent credential theft, LSAS is protected with PPL, Protected Process Lite, signed as PS Protected Signer LSA Lite. This protection level blocks attempts to dump its memory as seen in the error message. The operation could not be completed. Access is denied when we use Task Manager to dump LSAS. Now we will demonstrate how to bypass Protected Process Lite PPL on LSAS Local Security Authority Subsystem Service by modifying its protection level in the eProcess structure. This technique removes LSA Lite protection, allowing full access to LSAS memory, including the ability to dump credentials using tools like Mimikatz. So the first command will locate the LSAS eProcess address, and from that we will use the second command to view the protection level. In this case, it's on the offset 0x87A, and the level value of 0x41A in ASCII corresponds to the PS Protected Signer LSA Lite. Then in the third command, we will edit the protection level, setting it to 0x00, effectively removing the LSA Lite protection, and recheck its value in the fourth command to confirm its protection level removed. After all that, we can see that the protection level of LSAS is removed from the Process Explorer entry, and we managed to dump LSAS using Task Manager.